Welcome all. I'm just going to explain to you how to do the conduction experiment calculations. Okay, so the data I have is this one. A different different heating Q. Okay, so I have this. So at Q 13 watt, this is the temperature profile. So this is steady state temperature profile at different position, right? And same at three different watt heating. So what we are doing, we are in the linear conduction. uh, as you can recall that we have a cylinder and we are heating at this point, right? So this is Q. At here we have heater Q, constant heat, and then temperature we are measuring at different position. So temperature will drop due to thermal resistance, right? So if we have data with time, what does it mean? Like when we started the heater, this is time 0, t equals 0. After 5 minutes, after 10 minutes, after 15 minutes, 20 minutes, so the profile will build and we will reach the steady state. Okay, we need only steady state data for calculation. So if you have data with time, it means that just you need to plot it t versus x at different time. So maybe this one, first one is t uh, 10 or 15, and then next 15 minute, then 20 minute, then 25 minute. So what you will see that the profile are, as we time moves, the profile is overlapping. So what does it mean? There's no change in profile. It means that it is reaching a steady state. So you will take your last value, which is 25 minutes around. We assume that it will reach steady state. Okay, so this one is straightforward. Now you will just plot this data, t versus x at different watt. Okay, so what you will get, I'm not going to show you this one, easy. So what you will get steady state profile t versus x, three value, three graph. Okay, so as we move away from the heat source, temperature is dropping due to thermal resistance. And for each, using the trend line, this is linear for sure. So using trend line, you can get the slope, right? So what we have for linear conduction, we have Q equal Ka dt dx. So we have Q, we have dt dx slope for each Q. Area of the cylinder is known. You can find thermal conductivity. Okay, so thermal conductivity we can find for three data point. Okay, and thermal conductivity should not change, right? K values we have 1 2 3. So this is the it should be almost constant. You can find deviation to see how much is the standard deviation and so on. And then now what you can do, you can have three slopes, one two three dt dx. Okay, and then 3 dt dx, and to prove the Fourier law, at different q you have dt dx, right? Three data points, 1 2 3. So you can plot q versus dt dx. Okay, and what is Fourier law? So it says that heat applied is directly proportional to the temperature gradient minus. Okay, so temperature gradient, so we need to plot q versus dt dx, and then the slope of that plot will be qa, and area is known, so you can find q also here from this way. Okay, hope this is clear. Now linear is straightforward. You know, you have some doubt in radial. So in radial, what we have? We have inner cylinder. Okay, so this is basically Ri, and then from here we have outer. So we are measuring at different data points here. This is outer cylinder. Okay, so if you plot T versus R, this is not going to be linear. Okay, it's like this. So let me plot this one for then see this is uh, so at 28 when so if you plot this one. Okay, so what do you have? You have this, and so I need to add x-axis, which is radial position. Okay, so you can see it is something like this. So from the equation we see that that's the profile is logarithm. So this is the profile we have. Okay, how we know that lab manual. Okay, so this is the, you can see the profile T. If we say this T, this T, so this T outer, right? This is T versus R. So the relation to T is proportional to L and R. So this is logarithm profile. If we plot T versus L and R, then that is the linear equation. Okay. So now using the data now here radial data, how to find use this to find k value. So you can see you can use right away the equation ln r naught ri to minus ti. Okay, so for example what we have here, um, you can see for this one, so ln r naught is this one, this is r naught, ri is this is ri. So ln r naught divided by ri, okay, times q. In this case I have 28, and the equation is, okay, divided by 2 pi l. So divided by 2 times 3.14, the thickness 0.004, times the temperature difference. Okay, so temperature difference is this minus this, inner minus out, inner minus outer. Yes. Okay, so around 120 I am getting, and reference value is around 120, 125. Just check it. So this is one way we can find the thermal conductivity. uh, okay, this, hope this is clear. The other way is by linearizing. So linearizing what, ln r naught by ri. So now see the equation, how it will be, uh, ln r naught over ri, okay, equal 2 pi l k divided by q to minus ti. Okay, to minus ti. So now if we plot ln ro ln ro over ri, or ln r versus t, okay, or this. So we need to understand this. So ln ro, this is y axis, and this is x axis. So ti is the temperature of inner, we can assume is constant. To is outer, which is varying. Okay, so this is one is changing. So this versus this. So how we can do in Excel? So okay, this one I did it. Okay, I will do it again. Okay, so basically what we have, ln r naught. So ln r naught. So initially it is the inner one. Okay, this will change, right? So ln r naught divided by ln ri, which is the same. But this one I need to fix. Ri is constant. Okay, so this is varying. I will drag this one. So all the time we are dividing by the inner. So this is ln r naught divided by r. Okay, no, ln r divided by ri. Okay, and then we have t minus ti. Ti is constant, right? Ti is the first one. So first one means this one, right? So this one minus ti is this. Ti is constant, right? So ti, I will fix it. Okay, then it's changing. Is it clear? So this one, this is the temperature changing, and we are subtracting with the inner temperature, which is this. So first value will be 0, then it is negative, and then negative, negative, negative. Okay, what we need to do, we need to plot this one. This ln r, okay, this one, and then we have x axis ti. Okay, perfect. So now at the trend line, display. Now one question: what if I plot this versus this? Why this is y? Okay, play. This is y. Okay, and this is x. We need to learn this. So what is my equation for trend line? Y equal mx. Y equal mx. Where is c? No c. Intercept is 0, isn't it? Intercept is 0. In Excel, we can force the intercept to 0. Intercept to 0. This means we are really representing the real scenario. Okay. So what I did, I make this intercept 0. So now you can see there is no intercept. Okay. Slope I got is 0.1227. Okay. 0.1227. And I did this one for watt Q hitting 28. So now the slope of this is this 2 pi L and K is there, sorry, K, 2 pi L K divided by Q. So 2 pi L is the length or thickness basically, Q equals slope. Okay, So what will be the K? Slope times Q divided by 2 pi L. So okay, and the slope is this. So K will be, the K will be slope. Slope is 0.1227. Slope is, okay, so slope times q is 28 divided by 2 pi 3.14. uh, L is the thickness of the cylinder, 2004, right? 2 pi L, and that's yeah. So K, in this case, K is slope times Q divided by 2 pi L. Okay, so, and that's it. So I am getting 136. So from different methods, you will get different values. Okay, close values around 120, 130, 140. You can report all of them, find the average. Okay, find the standard deviation because we expect that K should be constant. Okay, and then you can report standard deviation of all. So with using different methods, suppose you have K, right? So using this, yani, you have 123.5, you have 134, you have 132, you have 129. We did linear, radial, all this. Okay, so what you can do, you can find the average and say this is my final experimental value of K, and then you can find a standard deviation because we expect that a standard deviation, this one, we expect that this will constant. So what is the value of deviation? 4.57, for example I have. So your final value of K will be 1.29.6 plus minus 4.57. This is the way to report experimental value. So it is like not very much. So for all practical purpose, our thermal conductivity value of brass is constant. Okay, hope this will help you. Thank you.